Welcome to Science or Fiction, a podcast by sci-fi author Michael James Scharen. In this program, we'll be discussing science, fiction, and the often blurred spaces between the two. Here we try to dispel common scientific misconceptions by both Hollywood and the media, even that which is meant to be educational. My background includes a Bachelor of Science and Master of Arts in Physics, with experience in both R&D and production. I hope you enjoy these podcasts, and if there are comments or input, please direct them via the contact page for my website, michaelsbookcorner.com. In this episode, let's delve into an ever more pervasive idea regarding the distribution of life in the universe. The theory I'm referring to is called Panspermia. Basically, panspermia is the notion that life on Earth or other bodies is distributed via physical transportation from one planet or moon to the other by way of asteroids. To be more specific, dormant microbes, or those which become dormant in rock, are ejected from the surface of one body into space to then be deposited when a meteorite lands on another body. In one program after another, and in several podcasts, this concept keeps popping up. No one could claim this scenario is impossible, but in not one program have I seen a serious analysis of the process. To begin with, panspermia is not really an explanation for the origins of life at all. It is a chicken and egg problem. Life has to have begun somewhere to set it all in motion. In evaluating ideas about the physical world, it's extremely useful to look at them in terms of probability. It is unfortunate that few people have ever studied probability and statistics. Even there, no hairy math is really required, and the point can be made in a straightforward fashion. The probability of any resulting event is the product of the probabilities for each separate event required in the chain leading to that outcome. That is a mouthful for sure. A simple example would be a person getting to work on time. This could be broken up into any number of requirements, such as 1. The car starting, 2. Traffic lights, 3. Road accidents, 4. Breakdowns, 5. Other traffic. The probability of getting to work on time is the product of 5 separate probabilities there. 1. The likelihood of the car starting. 2. The lights are with you or against you. 3. There is an accident blocking the road. 4. Is your car in good working condition? And 5. The time of day and traffic. Let's say the probability of starting is 98%. Traffic lights with you is 98%. No road accidents is 99%. No breakdowns is 92%. And impedance by other traffic is 98%. Just take all those probabilities and multiply them. So we have 98% times 98% times 99% times 92% times 98%. Mathematically, a probable certainty is given the value of 1 and probabilities, decimal values, less than 1. 98% corresponds to 0.98, etc. So now the probability of getting to work on time is 0.98 times 0.98 times 0.99 times 0.92 times 0.98 equals 0.857 or 85.7%. To make sure you get there in time, you tackle each of these areas according to relative importance, whether it is taking the right route, getting your car tuned up, or leaving at the appropriate time. We do this instinctively. Now let's look at panspermia. Let's assume planet A has life and planet B does not. On Earth, where life has firmly taken hold, we see it in nearly every environment. These include polar regions, natural hot springs, deep ocean vents, high in the atmosphere, and in rocks to great depths. This says much for the hardiness of life, but let's follow it through. A celestial object striking a planet like the Earth or Mars will likely be traveling at extremely high relative velocity, on the order of tens of thousands of miles per hour, much faster than a rifle bullet. The kinetic energy of the object is 1/2 times its mass times its velocity squared. This is why a deadly asteroid strike on Earth does not require a rock of tremendous size. The energy comes largely from that velocity squared term. Another principle of physics is that energy is conserved, meaning it doesn't go away but is only transformed. So the kinetic energy, or energy of motion, in the asteroid has to go somewhere. On striking the planet, it is quickly heated by friction in the atmosphere, then to the point of melting itself and much of the ground on impact. Where there are remains of the meteor after impact, we call these meteorites. Energy is also imparted to the surrounding impact crater as work. Work is energy required to move mass, so work translates to kinetic energy for the ejecta of the crater. Returning to our chicken and egg analogy, let's assume there are viable life forms within the asteroid. First, we have the probability of that even occurring. We have examples such as tardigrades or microbes that can survive the vacuum of space, as well as the radiation, but for how long? Next, the probability of any near the surface of the asteroid surviving entry into an atmosphere without incineration is slim. If life is deeper in the rock, the heat is still being transferred to the center. Next comes the impact, where nearly all of that kinetic energy is transformed instantaneously to heat. The energy of an asteroid strike is comparable to that of a thermonuclear device. One Defense Department proposal is a weapon called God's Rods, which would consist of a number of tungsten projectiles the size of telephone poles. Dropped from orbit, one of these could take out a city block. Past impact craters on Earth are estimated at tens or hundreds of megatons of TNT. Upon deceleration, most of the asteroid will become molten, along with the ground underneath. The first atomic bomb test at Alamogordo, New Mexico, left the site littered with glass beads formed from the fusing of desert sand at high temperatures. Sites in the Sahara have similar glasses, likely formed from impacts. The probability of any microbes surviving this collision have to be extremely small. Of course, if any microbes or multicelled creatures did survive the trip, then how likely is their new home to be conducive to further existence and propagation? One has to ask the question that if this new abode is so favorable to life, then why wouldn't it have evolved already? If it is not, then what are these invaders going to eat? There may be suitable places where photo or chemosynthesis is possible, but what if they did not land in the right place? We're talking about one or a few species arriving on one small portion of the planet, which could contain many different local environments. Organisms in general evolve in response to very specific environments. The chances of ending up in just the right one cannot be great. As one can see, the probabilities of each necessary step for panspermia should be considered low, based on actual observation. The prospect of naturally evolving life for each body must be far greater based on even limited information. It is an axiom of physics and chemistry that if something can happen here, it is highly likely that it will happen anywhere else with near equal conditions. Much of astronomy is based upon this fact. We measure the absorption spectra for various elements and compounds here on Earth. Then via probes and telescopes we see the same throughout the solar system and the universe at large. This is how we know the chemical makeup of distant stars or bodies in our solar system. The universe is made up of the same chemical elements and compounds which behave the same in a laboratory or millions of light years from Earth. Before 1995, there were no confirmed planets orbiting other stars, but there was no reason to believe their Sol system was unique. Now over 2,000 have been found. Even in the late 1970s, when Vikings 1 and 2 landed on Mars, the evidence was strong, as indicated by the labeled release experiment, that there appears to be life there. Indications for the processing of organic nutrients were present with the same procedure used at widely separated landing sites. This came in the release of tagged CO2 and methane from Martian soil, where the carbon atoms in the nutrients had been labeled with radioactive isotopes. These same isotopes were found in the gases released by something in the soil. Yet NASA declared there was no life on Mars and has not made any serious attempt at further testing since then. The only discussion of life on Mars since that time has been the farcical search for Martian fossils. Even there, the so-called search is not taking place in areas with a high chance of success. Fortunately, serious work on the chemical origins of life has continued from the time of the famous Miller experiment in 1952. This method created organic chemicals, including amino acids, from a primordial soup acted on by an electric discharge, simulating lightning. This attempt to mimic the natural formulation of such compounds was indeed speculative. However, with several deep space probes now confirming significant amounts of tholins on other bodies, the natural synthesis of amino acids has been verified. Tholins are layers of a reddish-brown mixture containing many different hydrocarbon compounds. They turn out to be a natural product of organic chemicals being combined in the presence of ultraviolet radiation in space, or the thin atmospheres of Pluto or Europa, as well as asteroids and comets. Amino acids are also present in the ice water plumes of Enceladus, emanating from a liquid ocean under kilometers of ice, not subject to ultraviolet rays. Heat is provided by gravitational forces kneading these moons like wads of bread dough. If you hold a piece of metal and keep bending it back and forth, you can feel it heating up, just like these moons. The same conditions existing on Enceladus may be present within deep oceans believed to be on Europa or Ganymede. Of course, Titan is covered in organics, even raining methane or ethane, which flow into rivers and lakes, giving rise to the question, are fossil fuels really from fossils? Very recently, the Foundation for Applied Molecular Evolution has reported the synthesis of ribonucleic acid, or RNA, with a reaction being catalyzed by basaltic or volcanic glass. Water percolating through the rock containing simpler constituents produces RNA, a molecule capable of reproducing itself, with two such strands making up DNA. The early Earth and Mars were sites of extensive volcanic activity. This is the result of both outside impacts and natural cooling of each body from the time of their formation. It has been hypothesized that life on Earth may also have arisen in the presence of volcanic fissures in the ocean. Organisms derive their metabolic energy from heat and the presence of the right chemicals rather than by photosynthesis. From exploration over the past 30 years, we know such areas have abundant life. Volcanic glass cannot be rare in the universe. It is my contention that life is a natural process given the laws of physics and chemistry. As such, it is likely more widespread than presently believed. Increasingly, we see the chemical constituents are present in many places, as well as energy and the existence of liquid water. Granted, there has been no discovery of a planet such as Earth with liquid water on the surface and a friendly atmosphere, but this may come in time. Perhaps the James Webb Telescope will make the first discovery. As stated above, if it can happen once in the universe, then it will likely happen many times over. In my lifetime, no one knew what a quasar or a pulsar was, or if they were rare. It turns out they were not. As a consumer of many a science program, specifically astronomy, I've seen trends and patterns across different productions which repeat each other, often with little or unsound backing. Panspermia strikes me as just such an idea. I hope they are not merely copying each other, but that is a topic I will be visiting in future podcasts. I hope you've enjoyed this program, written and presented by author Michael James Scharen, in conjunction with with my mini science fiction novels. Please visit the website, michaelsbookcorner.com, to see what is on offer. A new episode of Science or Fiction will be brought to you each week. Thank you for listening.